It's Past Paper Guy here. I'm going to be solving this GCSE Electronics paper from WJEC. It's the 2009-16 paper, and I'll put a link to the paper in the description below. As always with all of the papers, I strongly recommend that you print it off and have a go, and then look at this video to fix any problems that you had. So without further ado, we'll move on to question 1, where we have a basic circuit theory problem here. So we need to use Kirchhoffs laws in order to work all of these out. So what is the value of V1? Well, we need to get from here to here. It's a 9 volt total. We've got 2 volts here, so we need to go up by another 7 volts. 2 plus 7 will get us from 0 to 9. So that's got to be 7. Hopefully you can see that. My pen doesn't seem to be very bright. What is the value of I2? This is I2 here. So we've got 8 milliamps flowing this way. 3 of them are going that way, which leaves 3 minus from 8 gives you 5 milliamps to go that way. So that's got to be 5. What is the value of V3? Well, V3 is in parallel with V2, so both of those there have to have the exact same potential across them, so that's the 2 volts then. That's the same potential as that. It's not just the same value, it is actually the same potential. What's the value of I4? Well, all the current entering here must leave from here, so that is going to be 8 milliamps. You've got 5 there and 3 coming that way, leaving you with 8 milliamps there. Okay, question 2. Some simple questions to start us off with. So this one here you need to know is the diode. This one here is a variable resistor, so this one. And this one here, it's no longer on the spec, but it's the thyristor. You can work it out by process of elimination anyway, because a transistor is that. The thermistor is the one with the hockey stick through it, and the LED is like that, but with 2 arrows coming off it, so that's a thyristor. Okay, link each subsystem on the left to the correct function on the right. One has been done for you. So we've got a latch unit is a process. It wants you to know that a NOR gate is going to be a process, a motor is an output, a transistor switch will be a process, and a light sensing switch is going to be an input. Question 3, how many gates are there here? Well, there's 1, 2, 3, 4 gates. What type of gate are they? These are OR gates because they've got a curly back there. And what is the pin numbered X? So we start here because there's the notch. So we start here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is pin 11. My pen unfortunately is dying. Select the name of each gate. So this is a NAND because it's got the circle after it. This is a NOT, and this is an AND. I've had to change to pencil, so hopefully you'll be able to see this better. Question 5, we've got to label these 3 things on this here. So we want the positive supply, that's going to be this V+. We want the output, that's the one coming out of here. And we want the inverting input. The inverting one is the one with the minus sign. Okay, question 6. The diagram shows a 270 kilo ohm resistor. So that's 270,000 ohms. So we've got 2 and 7. If you use this here, you can see that that is red, violet, and then we've got 1, 2, 3, 4 zeros, which is a yellow. Okay, then we have here there are 4 lamps. we need to calculate the power in this lamp, and it says in watts, and we're doing it in lamp C, very confusingly, which is that lamp there. So P equals IV, which is equal to 400 milliamps times by 9. So we need to divide that by 1,000 in order to get it into amps, because it's 400 milliamps, so 400 divided by 1,000. So that's 0.4 times by 9. 0.4 times by 9 is 3.6. Oops, I already wrote that in. There we go. Then we need to find that on here. It's that one there. And question B, which two lamps have the same power? So this one is 3.6 watts. This one is 6 volts times by 0.15, which is 0.9 watts. This one is 12 volts times by 0.06. That's much smaller, isn't it? That's 12 sixes is 72. And then finally here we have 3 times by 0.3 amps, which is 0.9. So this one and this one are the same. So it's that one there. Okay, question 8. We have a sensing unit here, set up as a potential divider. So we'll circle the name of this component. That's an LDR. It's got the arrows coming in representing the light. If V out is 6 volts, then what's the correct voltage across component X? What is Vx here? Well, if 0 to 6, then we go 6 to 15, so that's got to be 9 volts to get from 6 to 15. What would happen to the voltage V out if a torch was used to shine light on the circuit? Well, an LDR's response is going to be like this. So as the light increases, which is what's happening, its resistance will reduce. So the resistance here will reduce, meaning that this voltage is going to rise. So V out would rise there. Give a reason, because as light shines on the LDR, its resistance reduces. So Vx will reduce and V out will rise. So if this voltage here reduces, then this voltage here must increase, V out. Okay, question 9. A garden centre requires an automatic system to water the flowers in the customer display areas. The system should switch on the water when the soil is dry and it is dark to avoid soaking the customers. It should switch off automatically when the soil is damp or it gets light. Okay. So we are going to need to make sure that we get all of these in. So that clue there gives you the fact that it is an AND gate. It's going to be needed here. So we can put an AND gate in here. And that comes straight from the question there. We're going to need some sort of driver for this. So we need one of these to be a driver, which that one will do nicely. If it had a transistor driver there, we could have put that one in there. Right, we're going to need one of these to be the moisture sensor unit, and we're going to need it to a light sensing unit as well. So we're going to have those two, and we're going to think here. So when the light sensor is 1, when it's daylight, we want it to be dark. So we want it to be a logical 0 when it's dark. The moisture sensor is a 0 when it's wet and 1 when it's dry. So we can put the moisture sensor straight in here. and this one's going to give us the logical 0 when we want it to turn on. So if we put that here, we're going to also need a NOT gate here. It doesn't say, but it does say inverter, so we can put that in. Like so. Circle the logic gate that has the following truth table. That's a NAND gate. An AND gate would be this, and it's the opposite of that, so it's a NAND gate. Circle the logic gate that outputs a logical 0 only when both inputs are at logical 0. So that would be this, wouldn't it? It would be 0, 1, 1, 1, like that. So that's question B. Yep, so that is an OR gate. So that's there. Logic system has the following truth table. So point X is going to be if we look at X here and we compare that to A, it's the opposite of A. So we shove in a NOT gate here. We want point Y, and we compare that with this here. Point Y is the opposite of B there, so that also gets a NOT gate there. Now we need to compare these two to get to here, and that is only when they're both 0. Is it a 1? So that is a NOR gate. So we want this one here. Like so. Let's just check that. So 0, 0, 0, 1, 1, 0, 1, 1. So an OR gate would be 0, 1, 1, 1, and a NOR gate, that's an OR gate, would be 1, 0, 0, 0. So when they're both 0, we get a 1, and any other combination, we get a 0. So yes, it's a NOR gate. Circle the single logic gate that could replace the above combination. So all of this going straight to that, that's an AND gate, isn't it? Some of the NAND gates in this logic circuit below are redundant. Circle the redundant ones. So we want one, when this configured like a NOT gate like this, it's when two are following each other. So we've got two following each other there. They cancel each other out. We've got two following each other there. They cancel each other out as well. The diagrams below show three different combinations of two resistors. Calculate the effective resistance of each combination. Okay, so we just need to add these together because they're in series. Remembering this is 300 and that's 1,800, so that's 2,100. It wants it in kilo ohms, so that's 2.1 kilo ohms. If you wrote 2,100 ohms like that, you'd get the right answer, because as long as you've changed the unit, you'd be okay. This one here, there's a shortcut to this one. If you've got two resistors which are the same, if they're in parallel, you can just take the resistor and divide by the number that there are. So it's 82 divided by 2, which is equal to 41 kilo ohms. So that's going to be 41. And this one here, we can do it one of two ways. We can do 1 over R total is equal to 1 over R1 plus 1 over R2, which you'll find on the formula sheet. No, you won't. This is the shortcut. If you've got two resistors, you can do this. R total is equal to the product, so R1 times by R2 over the sum R1 plus R2. So you can do either way with these. This way is a little bit easier when you've just got two resistors. So we're going to have 3,600 times by 2,400 divided by 3,600 plus 2,400, and that's going to be R total. It's going to equal that. So that's a total of 6,000 on the top. 6,000 on the bottom. So we've got 3,600 times by 2,400 divided by 6,000. So what's that? That's 8640000. Gives us a total of 1,440. So that's 1.44 kilo ohms, which is the final answer. Now, as a check, you can just check that has to be smaller than the smallest of those two, which it is. So we're okay. Here are two truth tables. Select the correct Boolean equation that represents the function described in each truth table. So here we have not A and not B. So not A and not B. Here we have not A and B, or A and not B. So not A and B, or no, that's not it. Not A and B, or A and not B. It's that one there. The following show NAND equivalents of some standard gates. So this is the NOT gate. This one here is an AND gate. It's a NAND followed by a OR. This one here is, one of these is the NOR and one of these is the NOT. So let me just do a, so this is not A ANDed with not B, all NANDed, which if you use De Morgan's theorem on that, is that. So that's the OR gate, and that one is the NOR gate. So to answer the question, this needs to be A, this one needs to be D, and this one needs to be C. Following shows part of a burglar alarm. The input A needs to be a logical 1 when a switch is, logical 0 when a switch is pressed. Draw the components required. So we want it to be 0 when pressed. So we need the switch to be down there, and then we need a pull-up resistor here to make it 1 when the switch is not pushed. What is the purpose of the component labelled Y? So that is pulling B down. So that is a pull down resistor for B. That will be good enough. What it does is it means that the voltage at B is equal to 0 volts when the button is not pushed. So that will get you the marks, pull down resistor for B, but that's what it's doing. So it makes this voltage 0 when that is open. Otherwise, if you didn't have it, then B would float, and so it could be any value. The following incomplete circuit shows a comparator used to switch the floodlight on when it gets dark. Select the correct formula for the voltage Vref. So we've got the potential divider equation, which is V out is equal to V in times by R2 over R1 plus R2. So this one is R2, so it's going to equal V out, which is V in, which is 30 volts there, times by this, which is 1.5 times 10 to the 3, divided by both of them added together. So 1.5 plus 6, all times 10 to the minus plus 3. So those cancel, and we get 1.5 over 1.5 plus 6. So it is this one here. Just check that that's wrong, that's wrong, that's wrong. So it's that one there. Calculate the voltage Vref. So we have 30 times by 1.5 divided by 7.5 is equal to, that goes into that 5 times, so that's equal to 6 volts. 6 volts. Complete the output circuit for a comparator using the components shown below. Right, so we need to put a transistor in here and we need to put something in here. Now if we used an NPN transistor here, we'd need a resistor here, but they haven't allowed us to have a resistor, because you always have to have a base resistor for a transistor, like this sort of transistor. So we can't use that. You shouldn't even know what these are really, they're thyristors, but they're just there as red herrings. So we've got to put in the MOSFET here. So we'll have our MOSFET. Now the thing about the MOSFET is it does not need a base resistor, so we can just use a piece of wire to connect those two, like so. An LED is used as a power indicator as shown below. The LED requires a current of 16 milliamps, so it's a good idea to draw that on the diagram straight away. What's the voltage across the resistor R? So we've got 0 volts here, 12 volts here, and this is at 2 volts here, so that means that that's got to be 10 volts, doesn't it? 0 to 2, 2 to 12 is 10. Select the correct equation to calculate the ideal resistance of R. So we're going to use R is equal to V over I, which is equal to 10 divided by 16 times 10 to the minus 3. And it's going to be in kilo ohms. So that times 10 to the minus 3 will make it into kilo ohms. So it's going to be 10 over 16 here. That one there. Calculate the ideal resistance of R. So we have 10 divided by 16 is 0.625 kilo ohms. And then the current must be less than that. We now need to pick an E24 series resistor to make that work. So we have to pick the next highest up, and it says in ohms. I'm mixing the units up on us for some reason. So we can't have that one because that would be 620, and this is 625 ohms here. So we've got to go to this one, the next highest, because it has to be less there. So that's 680 ohms. And there we are, end of paper. Little Teddy is going to congratulate you for seeing it all the way through to the end. Hello, well done, good luck on your exams.